Okay, so our learning objective this time is that we want to write an expression for the nth term of a sequence, and in particular, we're going to look at arithmetic and geometric sequences. Notice I said arithmetic, not arithmetic. Spelled the same way, but we actually say arithmetic when we're looking at a sequence, and then geometric, it would be their type of sequence. Now, if you remember that we've come across these terms before, at some point in time, you learned that for an arithmetic mean, you would add up the list of numbers, count how many numbers there are, and then divide. And then for the geometric mean, you would multiply numbers together and then take a square root. So just like there's two different types of a mean we can find, arithmetic and geometric, same thing with a sequence. We can have an arithmetic sequence, we can have a geometric sequence. So if it's an arithmetic sequence, it's a pattern where we're adding. And more specifically, we have to add the exact same number every single time. So it can't be a pretty pattern with addition, like, oh, first I add 1, then I add 2, then I add 3, then I add 4. No, that's not arithmetic. I have to add the exact same thing every time. Geometric, instead, is a multiplication pattern. I have to multiply by the exact same thing every single time. So I can't multiply by 1 and then multiply by 2 and then multiply by 3. That'd be a pretty pattern, but it's not geometric. For geometric, I have to multiply by the exact same thing every single time. So if we want arithmetic, the nth term is always d times the quantity n minus 1 plus a sub 1. A sub 1, of course, is the first term in the sequence. D is the common difference. If this makes absolutely no sense at the moment, wait till we do an example with actual numbers, and then it'll probably become more clear exactly what is going on here. Same thing for geometric. If this just looks like gobbledygook at the moment, have patience. We'll do a couple of examples with actual numbers. But for the nth term of a geometric sequence, a sub n equals a sub 1 times r raised to the n minus 1. Notice only r is raised to the n minus 1, not the whole expression there. A sub 1, of course, is still your first term in the sequence, and r is the common ratio, the number you're multiplying by every single time. Please remember, if I'm ever going too fast, you can pause or stop the PowerPoint. You can rewind it, whatever you want to do. So let's take a look at some examples with numbers, and that will probably make a lot more sense. Okay, so here's a wonderful sequence, right? 7, 10, 13, 16, 19. And so it looks like every single time to get the next number, I want to add exactly 3. So it's arithmetic because I'm adding the exact same number every time. I always add 3 to get the next term. So D is 3. That's my common difference. Right? 10 subtract 7 is 3. 13 subtract 10 is 3. 16 subtract 13 is 3, etc. And of course, the first number in the list is 7, so we say that a sub 1 is 7. Now, on the previous slide, we said, hey, this is the generic formula that we're going to use, the generic equation. A sub n equals d times n minus 1 plus a sub 1. Well, we know d is going to be 3 because we added 3 every time. We know a sub 1 is 7 because that's the first number in the list. And now, well, can we simplify? Well, distributive property, right? 3 times n is 3n. 3 times 1 is 3. Oops, there's a negative in between, so it needs to be 3n minus 3. And just like we observed on Tuesday, yes, this is linear, right? This is like y equals mx plus b, right? The slope is 3. We went up 3 every time. And if we graphed it on an xy coordinate system, well, if it was a line, the y-intercept would have been 4. Right? Check it. Plug in the number 1. 3 times 1 is 3, plus 4 is 7. Try the number 2. 3 times 2 is 6, plus 4 is 10. So arithmetic, you could probably actually figure out the equation just off the top of your head, because it's basically just, linear equations, slope-intercept. Okay, now, is this one also arithmetic? Yes, it is. I'm claiming that I'm adding the same number every time. I'm adding -8 every time. Notice I don't think of this as subtraction. I don't think that I'm subtracting 8 every time. I'm thinking that I'm adding -8 each time. Right? 23 plus -8 is 15. 15 plus -8 is 7. 7 plus -8 is -1, etc. Or if I think about subtraction, 15 subtract 23, aha, -8. 7 subtract 15, ooh, that's -8. So it's arithmetic because I'm adding the exact same number each time. I'm always adding -8. First number in the list is 23. So again, if I just grab my generic expression there, d is -8. First term is 23. Use the distributive property. A little bit trickier this time because I've got that negative on the 8. So I've got to do -8 times n, which of course will be a -8n. And then the -8 times the -1, that has come out as a +8. Again, this works like any old linear equation. We added 8 each time. I'm sorry, we added -8 each time. And if we tried to graph this as if it were a straight line, right, if we ignore the fact that it was a sequence and just pretended it was a straight line for a moment, y equals mx plus b, it would intersect the y-axis at 31. Of course, with the sequence, we start by plugging in the number 1, right? We're not going to plug in the number 0. We start by plugging in the number 1. Okay, another fantastic example. And it looks like this time, every single time, to get the next number in the list, looks like I'm multiplying by 2. So it's a geometric sequence because I keep multiplying by the exact same number over and over. If you're having a hard time trying to figure out what number you're using to multiply, look at the numbers in the list. 6 divided by 3 is 2. 12 divided by 6 is 2. 24 divided by 12 is 2. So if you're ever not quite certain, just do the division that way. Divide each term by the previous one, and if you keep getting the same number, then you'll know it's geometric. So we know the ratio is 2. We keep multiplying by 2. We know the first number in the list is 3. So let's grab our equation. A sub 1 is going to be 3. R is going to be 2. And the nice thing about geometric is that there's no simplifying here. We're done. Let's test it out for like the fourth term. We know the fourth term should be 24. So plug in a 4 and see what happens. N minus 1 would be 4 minus 1. Well, 4 minus 1 is 3. So you'd have 2 to the third power. 2 to the third power is 8. 3 times 8 is 24. Now again, if I'm discussing and you're not following along, you can always pause the video and then actually try work this out with pencil and paper, right? Actually plug the number 4 in for n and confirm that indeed you come up with an answer of 24. Again, this is geometric because I'm multiplying by the exact same number each time. Notice that I claim this is multiplication. I think of it as multiplying by 1/3. I do not think of it as dividing by 3. Right? At first glance, it looks like, hey, we're dividing by 3 each time. But I want to think of it in terms of multiplication. So every single time I multiply by 1/3. Now again, if you can't eyeball that, try dividing. Take 81, divide it by 243. If you've got a calculator that reduces fractions, it'll say 1/3. Or if it comes out as a decimal, it'll be 0.333333 with the 3 repeating. Same thing if you do 27 over 81. 27 over 81 also reduces to 1/3. If I try 9 over 27, that also reduces to 1/3. So I know the ratio is 1/3. I keep multiplying by 1/3. I know the first number in the list is 243. And so I'm going to have 243 times 1/3 to the n minus 1 power. Again, if you aren't too certain that this really works, try plug in 1 for n, see what you get as an answer. Plug in 2 for the number n, see what you get for an answer. Plug in 3 for the number n, see what you get for an answer. So the big goal today, we're going opposite direction of last class. Last class, I would give you the equation for the nth term, and then you would try to plug in numbers and get like the first 6 terms. We're going the opposite direction. I'm showing you the list of numbers this time, and instead you got to try to come up with the equation. Most students find that this is going to be a little bit trickier. Previous class went very, very well. Now we got a couple of weird curveballs coming up here. On rare occasion, we start with a sub 0 instead of a sub 1. Now, unless you're told directly to start with 0, just assume you're going to start with 1. And then recursive means that we have to know a previous term or previous terms. Right? We don't just get a neat little equation where we can plug in numbers. We have to know what came ahead. And then all other terms are defined using the previous terms. My hunch is you've maybe already seen one of these before. Very well-known example is the Fibonacci sequence. For the Fibonacci sequence, we have to be told the first couple of terms. Notice they actually called the first term as a sub 0, so it's actually the 0 term. And then the first term is 1. I need a little bit of extra room there. So I'm going to go and I'm going to find the first, 10 terms, but remember we start counting at 0. So if I'm going to find the first 10 terms, I'm actually going from 0 to 9. Well, we know the very first number in the list, a sub 0, has to be 1. So I know that a sub 0 is 1. Of course, we're also told that a sub 1 is 1. Now, how am I going to figure out a sub 2? Well, if I want a sub 2, I'll have to look at a sub 2 minus 1 plus a sub 2 minus 2. Right? Our equation says if I want the nth term, look at the n minus 1 term, and look at the n minus 2 term. So if I want the second term, a sub 2, I have to look at term number 1 and term number 0, which of course would be 1 plus 1. So I now know that a sub 2 is 2. A sub 3? Well, I have to look at 3 minus 1 for that term, 3 minus 2, that term. So if I want a sub 3, I need to add up a sub 2 and a sub 1. So I've got to add 2 plus 1. That's 3. If I want the fourth number in the list, well, 4 minus 1 is 3. 4 minus 2 is 2. So if I want a sub 4, I need to look at a sub 3 and a sub 2. So 3 plus 2 is 5. If I want the fifth number in the list, a sub 5, I take a look at a sub 4 and a sub 3. 5 plus 3 is 8. Of course, this is how the Fibonacci sequence works, right? 1 plus 1 makes 2. 1 plus 2 makes 3. 2 plus 3 makes 5. 3 plus 5 makes 8. So I should be able to guess at this point that 5 plus 8 is 13, right? The next one's got to be 13. Let's see if that's what happens. A sub 6, is it really going to be 5 plus 8? Yeah. Because I need one term before number 6, which is 5. And then I need to look at 2 terms before number 6, which is 4. And sure enough, 8 plus 5 is 13. So if I want a sub 7, I got to add a sub 6 plus a sub 5. I've got to add 13 plus 8. That's 21. Now I get the hang of it. I want the 8th term, a sub 8. Well, the 2 preceding were 21 and 13. That makes 34. A sub 9. Take a look at the 2 previous terms. 34 plus 21, 55. So that's how recursive works. Someone has to tell me either the first term or maybe the first 2 terms, or in some cases maybe even the first 3 terms. And then they give a rule that refers back to the previous terms. Again, Fibonacci sequence, it's kind of unusual. They have us start with term 0. But in general, unless you're specifically told to start with 0, let's also assume we're going to start with 1. Now, sometimes weird things happen. It's not arithmetic, it's not geometric, and we got to try to figure out what's happening. So here is a wonderful list of numbers. 1, 4, 9, 16, 25, 36, ... so it keeps going. It's not arithmetic because we added 1, and then we added 5, and then we added 7, then we added 9. So it's a pretty addition pattern, but we didn't keep adding the exact same number every time. It's not multiplication because 1 times 4 is 4, but 4 times 4 does not make 9. 9 times 4 does not make 16, so obviously we're not multiplying by the same number each time. Do you recognize this list? Do you recognize these numbers? What kind of numbers they are? If you haven't quite figured it out yet, 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. It's just n squared. A sub n equals n squared. Right, so guess and check, rewrite the terms, look and see if it's maybe a list of numbers you've seen somewhere before. Or maybe it gets really weird. Again, at first glance, I'm wondering, do I add the same number each time? No. Am I multiplying by the same number each time? Nah. Right? 4 times 2.5 makes 10. But 10 times 2.5 would be 25, so no, we're not multiplying by the same number. What on earth is happening? Well, what if I rewrite 4 as 3 plus 1? What if I rewrite 10 as 9 plus 1? 28 is 27 plus 1. 82 is 81 plus 1. 244 is 243 plus 1, etc. 3 to the first plus 1, 3 squared plus 1, 3 to the third plus 1, 3 to the fourth plus 1, 3 to the fifth plus 1, 3 to the sixth plus 1. So the nth term is 3 to the n plus 1. Now, on the practice we're about to have, you might find one of them is like really crazy or really like impossible to figure out. But remember, the focus here is we want to look at the arithmetic sequences, the geometric sequences, and then, of course, recursive might show up and something weird might show up. Right? So we're going to have 8 practice questions. And to kind of give you some hints so you know what you're looking for, 3 of the 8 will be arithmetic. Right? So you'll be adding the same number each time. Remember, you might be adding a negative number, or you might be adding a decimal, or you might be adding a fraction. But 3 of those 8 will be arithmetic. 2 of the sequences are geometric. So that's over half the practice right there. That's 5 of the 8. So that should boost your confidence level up and say, hey, I should be able to do the arithmetic. I should be able to do the geometric. Right? That's 5 of the 8. At least one of the sequences is recursive. And then my hunch is the last question, or maybe the last 2 questions, it might take a while. Right? No fair getting too frustrated. Sometimes if you worked for like 5 or 10 minutes and you feel like you're just stuck, sometimes it's good to take a break, walk away, come back and look at it later. And if it gets to the point where you just cannot figure them out, well, I might have to give you some hints, or I might have to work with you. Next class session, we might want to take a look at them. Right? I won't leave you hanging forever, but my hunch is that probably the first 6 questions you're going to buzz right through quite well, especially the arithmetic and geometric ones. The last one, or maybe the last 2, well, you just might have to really get creative. Again, if you want to rewatch the PowerPoint, go for it. At any time, if I was going too fast, you can also, pause, stop, replay. Or if I was just kind of like talking and not showing the work, guess what? Grab pencil and paper, replay it, listen to what I say, hit pause, write down what I said. Play a little bit more, hit pause, write down what I said, right? Go with pencil and paper. Okay, time for me to sign off. Time for you to start working.